Okay, 1.2, Objective 2, Polynomials. So now the mathematical models at which we'll be looking are polynomial. Function p is called a polynomial function if p of x is all of that. Now that is quite an expression right there. Might help to remember that all we're really looking at here is a sum of ax to the n's, ax to the n's, ax to the n's, where n is a non-negative integer and the numbers a naught, a1, a2, da da da, up to an are constants called the coefficients of the polynomial. But it's just a bunch of ax to the n's, and so if you just remember that, it's just a polynomial function in one variable. You can kind of take away some of the mystery here. Part of the reason that they write it this way is that they want to make a strategic use of this n right here in their definitions. Here's a fact to remember. Suppose you're doing your work and the problem is, what's the domain? It's likely to be a sub-problem in the homework set. What is the domain? Well, if it's a polynomial function, then the answer is automatic. The domain is a set of all real numbers. If the leading coefficient, a sub n, is not equal to 0, okay, in other words, that would make the highest power on x this n, then the degree of the polynomial is n. So n is the degree. For example, for this polynomial function p of x here, the degree is 6, because that's the highest power on x. And yes, that is a polynomial function, even though it has a square root in it, because we're not taking the square root of x, we're taking the square root of 2, and that's just a constant, right? That's just the a naught. That's just the last constant at the end. A polynomial of degree 1 is of the form p of x equals mx plus b, and so it is a linear function. If it is of degree 2, that is, if it has the form p of x equals ax squared plus bx plus c, it is called quadratic function. Never mind the true meaning of the root quad. A quadratic function's graph is always a parabola obtained by shifting the parabola y equals ax squared. For a positive, it's going to open upward, and for a negative, it's going to open downward. For a big, that is in absolute value, it's going to be a narrow parabola. For a little in absolute value, like 1/2, it's going to be a wide parabola. A polynomial function of degree 3 is of the form ax cubed plus bx squared plus cx plus d, a not equal to 0, and is called a cubic function. Figure 8 shows the graph of a cubic function in part B, and the graphs of degrees 1 and 5 in parts A and C. So here's the polynomial function of degree 1. Here's the polynomial function of degree 5. And so you can see, okay, this is degree 1, degree 3, degree 5, and the polynomial function of degree 3 is like that of degree 1 except with an extra blip in it. The polynomial function of degree 5 is like that of degree 3 except that it has an extra blip in it. Example: a ball is dropped from the upper observation deck of the CN Tower 450 meters above the ground, and its height h above the ground is recorded at 1 second intervals in Table 2. Find a model to fit the data and use the model to predict the time at which the ball hits the ground. Okay, so you're dropping the ball, time goes by, the height of the ball decreases. And so when we are to find a model, okay, so that's the problem. Find a model. Then we're going to do something with it. But when we're told to find a model, the first thing we want to do is look at a scatter plot. Let's take a look at the scatter plot. We draw a scatter plot of the data in Figure 9 and observe that a linear model is inappropriate. It wouldn't be, the worst thing ever to try to fit a line to this set of points. It wouldn't be the worst thing ever. You could make predictions with it. But you'll see that it looks as if the data points might lie on a parabola. Would be better. So we try a quadratic model instead. And it was just the eye test. It was just because it looked curvilinear that a curve would fit that better than a line. Using a graphing calculator or a computer algebra system which uses the least squares method, okay, and these would be the keystrokes for that table that we've been given. Okay, if you want the calculator to give you a quadratic model, those would be the keystrokes for it, where I've kind of abbreviated the process just for the sake of space and time. You can see that I didn't input all of the ordered pairs, but just the first three. There's the 0, 1, 2. And here's the 450, 445, 431. So I only input the first three ordered pairs. And so the quadratic model that I got from that was slightly different, but if you input all the data, we obtain the following quadratic model. H equals 449.36 plus 0.96 t. I'm taking it that S just kind of sneaked on there and didn't really belong there, so I'm just going to take it off. I don't really see why anything else would be there. Minus 4.9 t squared. In Figure 10, we plot the graph of equation 3. Okay, so that thing that we just got from the calculator, we graph it together with the original scatter plot that we had, and this quadratic model gives a very good fit. In fact, it's so good, a student might think that those are necessarily points on the graph of the function that we got from the calculator. But no, they are not exactly, those points are not exactly on that pink line. Okay, the pink line is just an extremely good model, and makes we would expect it to make very good predictions. But those points are off the line. Okay. I would say the data set lend themselves well to the quadratic model. Probably too well, probably artificially well. The ball hits the ground when h equals 0, right? That's the height when we're on the ground, h equals 0. So we're going to set the height equal to the function. Okay, so the height function is on the left. We're going to set that equal to 0, and we're going to solve for t, and that will tell us the amount of seconds t that go by until the ball hits the ground. Quadratic formula gives this. Okay, so it was quadratic. H was a quadratic function of t, and so we find the a, the b, and the c. The coefficient of the squared term, right, which is going to be the negative 4.9. The coefficient of the linear term, t to the first, which is the 0.96. And the constant in the expression, which is the 449.36. And calculate minus b plus or minus square root b squared minus 4ac all over 2a, and we get this. Okay, there's a positive number and apparently a negative number, but we of course are going to reject the negative because you can't have a negative number of seconds after you drop a ball from a tower. The positive root is t approximately equal to 9.67, and now, answering a word problem of words because we want credit, we predict that the ball will hit the ground after about 9.7 seconds.